Welcome to the deep dive. Today we're venturing into, well, a really fascinating area of mathematics. It's this idea, which seems odd at first, that there isn't just one infinity,
Right.
but that some infinities are actually genuinely larger than others.
It's a big concept. We'll explore that and then look into non-standard analysis.
Yes, exactly. Non-standard analysis, and specifically the work of Terence Tao, who offers this unique way to sort of handle these infinite quantities.
It really is a revolutionary idea, this hierarchy of infinities.
Yeah.
For centuries, infinity was often just the single boundless thing.
Just infinity.
Just infinity. But then George Cantor, late 19th century, his work just shattered that, showed infinity comes in different sizes. It's foundational, really.
Okay, so that's our mission today. Unpack this. We've got sources like mathematics labor texts, Wikipedia on Cantor and Hilbert's Hotel, a bit from Reddit, Stanford Encyclopedia for set theory basics.
And crucially, insights from Terence Tao himself on orders of infinity and non-standard analysis, plus the overspill principle.
Right. So let's start with the basics. Countable versus uncountable sets.
Definitely the place to start.
Yeah.
So a set is countable if you can basically line up its elements one by one against the natural numbers 1, 2, 3.
Like a perfect pairing.
Exactly, one-to-one correspondence. Think of two infinite clubs. If you can pair up every member perfectly, no one left out, they have the same size.
Even if they're infinite.
Even if infinite. And surprisingly, like our sources mention, even sets that seem huge, like all the even numbers, still countable.
How does that work?
Simple. Pair natural number n with twocondim. 1 goes to 2, 2 goes to 4. Perfect match.
Okay.
Even the rational numbers, all the fractions, they're also countable. That pairing is a bit trickier to show, but it exists.
Yeah, that feels really counterintuitive. You'd think there'd be way more fractions jammed between the whole numbers.
It does feel that way, but mathematically, same size of infinity as the natural numbers.
Okay, so then uncountable sets. What makes them different?
Uncountable sets are the infinite ones, where that perfect pairing with natural numbers is just fundamentally impossible. You can't line them all up.
And the classic example is
The real numbers, all the numbers on the number line, including decimals that go on forever non-repeating, like pi.
Right. And Cantor proved this with the diagonal argument.
Precisely. The diagonal argument explained well in Libre texts and Wikipedia is just elegant proof.
Can you give us the gist? How does it work broadly?
Sure. Imagine you try to list all the real numbers, say, just between 0 and 1, an infinitely long list. You think you've got them all.
Okay.
Cantor shows no matter how you make that list, you can always construct a new real number between 0 and 1 that you definitely missed. Guaranteed.
How?
You look down the diagonal of your list, digit by digit. For the first number, look at its first decimal digit. For the second number, the second digit, and so on.
Along the diagonal.
Exactly. Then you create a new number. Make its first decimal digit different from the first digit of the first number on your list. Make its second digit different from the second digit of the second number.
Ah, so it's guaranteed to be different from every number on the list in at least one spot.
Precisely. Which means your list, no matter how you made it, couldn't have been complete. There's always at least one missing.
Wow. So no list can ever capture all the real numbers.
Yeah.
That really drives home that it's a different, bigger kind of infinity than the natural numbers.
It absolutely does.
And this idea, it connects to power sets too, right? The set of all possible subsets.
Yes, Cantor's theorem. The Stanford Encyclopedia mentions this. For any set, finite or infinite, the collection of all its possible subsets, its power set, is always strictly larger in cardinality.
So you take the natural numbers, its power set is a bigger infinity. Take that set, its power set is bigger still.
Exactly. It generates, as one Reddit user put it, a whole stack of infinities that get bigger than the one before. An infinite tower.
Mind-boggling. Okay. To grapple with this weirdness, especially with the countable kind of infinity, Hilbert's Grand Hotel is a great illustration.
Ah, yes. The Grand Hotel. Classic thought experiment.
Walk us through it.
Okay, imagine a hotel. It has infinitely many rooms, numbered 1, 2, 3, and so on. And tonight, it's completely full. Every room occupied.
Infinitely full. Seems like a problem if someone new shows up.
You'd think. But then a new guest arrives. Can the hotel accommodate them? Yes.
Wow.
The manager just asks everyone to move one room down. Guest in room 1 moves to room 2, room 2 to room 3, room n to room +1.
And that frees up room 1.
Clever.
Exactly. Room 1 is now vacant for the new guest. But it gets weirder. What if an infinite number of new guests arrive? Say, a countably infinite busload pulls up.
Well, that seems impossible.
Still possible. This time the manager asks the guest in room N to move to room 2.
So room 1 goes to 2, room 2 goes to 4, room 3 goes to 6. Right. That fills up all the even-numbered rooms, but leaves all the odd-numbered rooms, 1, 3, 5, 7, infinitely many of them completely empty for the new arrivals.
That just breaks my brain's concept of full. A full infinite hotel can always take more.
It highlights how properties of finite sets just don't carry over neatly to infinite ones.
And which brings us to cardinality. That's the formal way to measure the size of these sets, right?
Exactly. Cardinality. Two sets have the same cardinality if you can find that perfect one-to-one matching, the bijection between them. We write A by B.
And if you can map A into B 1-to-1, but maybe not fill up all of B.
That means B is at least as large as A. We write AAB, an injection.
Okay. And there's a theorem, Schroeder-Bernstein.
Right. That's a powerful tool. It says if you can show AAB and BA, then they must have the same cardinality AAB, even if finding the actual bijection is really hard.
So you don't need the explicit perfect pairing, just proof that mappings exist in both directions.
Precisely. It's how we know, for instance, that the rational numbers have the same cardinality as the natural numbers. Elif null. We can map naturals to rationals easily and show a map from rationals back to naturals.
So naturals, rationals, a case. But then, as Cantor showed, the reals are bigger.
Yes, the cardinality of the reals, often called C for continuum, is strictly greater than area.
Okay. Now, let's shift gears a bit. This is where Terence Tao's perspective on non-standard analysis comes in. Traditional calculus uses limits, epsilon delta. It can get complex.
Very complex. Lots of epsilon management, as Tao puts it.
So what does non-standard analysis do differently? Tao says it sort of rearranges the foundations.
That's a good way to put it.
Yeah.
Instead of focusing solely on limits approached indirectly, non-standard analysis introduces a larger number system, the hyperreals.
Hyperreals.
Yes. Think of the standard real numbers, but now you also have actual infinitesimal numbers, infinitely small, closer to 0 than any standard real number, except 0 itself, and also infinite numbers, larger than any standard real.
Whoa. Actual infinitesimals, like Leibniz originally thought.
In a rigorously defined way, yes. And within this hyperreal system, you can treat things like orders of infinity more, algebraically.
How so?
Well, these orders of infinity, within this framework, they form a structure like a totally ordered vector space. You can manipulate them more directly using algebraic rules rather than constantly managing limiting processes.
So instead of complex epsilon delta proofs about limits, you might be doing algebra with infinite and infinitesimal numbers.
That's the core idea. It aims to make analysis feel more algebraic.
And a key part of this is the transfer principle.
Absolutely crucial. The transfer principle is like a dictionary. It says that any elementary statement that's true about the standard real numbers is also true about the hyperreal numbers, provided you interpret it correctly within that larger system.
Elementary meaning?
Roughly, statements expressible in first-order logic using standard relations like plus, h, eta, covers a vast amount of standard mathematics.
So you can take a statement about, say, asymptotic behavior, how functions grow, translate it into the language of non-standard infinite numbers using the transfer principle.
Perform algebraic manipulations on those non-standard quantities, and then potentially translate the result back into a statement about standard asymptotics.
That sounds potentially much simpler for certain problems.
It can be, especially for proving the existence of certain asymptotic relationships.
But Tao mentions trade-offs. It's not a magic bullet. What's the price to pay?
Well, one major aspect is the nature of these hyperreal number systems. They are huge. Mathematically, they're non-separable, not countably generated, much more complex beasts than the standard real line.
Okay, so the underlying structure is more complicated. Any other drawbacks?
Another point Tao raises is extracting concrete information. Non-standard analysis might tell you easily that function f grows faster than g asymptotically.
Right.
But getting this specific constant in fx, z, gx, or the precise rate of decay for an error term, that can sometimes be harder than with traditional methods, which often build those constants in from the start.
So it's great for the algebraic structure and existence proofs, maybe less so for pinning down exact numerical bounds sometimes.
That's a fair summary of the trade-off. Different tools for different jobs.
Where might this algebraic approach really shine then? What are the potential benefits?
Tao suggests symbolic computation. Think about computer algebra systems like Mathematica or Maple. Trying to get them to rigorously handle and simplify expressions involving orders of growth, like big O notation, can be tricky. The algebraic nature of non-standard analysis might offer a more formal, more robust way to implement those kinds of computations.
Interesting. Making automated reasoning about function growth more powerful.
Potentially, yes. And related to that, others have pointed out the possibility of using proof assistance tools like Coq or Isabelle HOL to formally verify results within non-standard analysis.
So building machine-checked proofs using these infinitesimals and infinite numbers.
Exactly, which could be very valuable for complex asymptotic arguments.
Okay, one more piece from the non-standard world. The overspill principle. What's that about?
Right, overspill. It's another key property connecting the standard parts of the hyperreal universe to the non-standard parts. It essentially says if a property holds for all standard finite numbers within the system.
Like for 1, 2, 3, all the way up.
For all standard natural numbers, then that property must also hold for at least one infinite hypernatural number. It has to spill over into the infinite realm.
So you can't have a property that holds for all finite integers but no infinite ones.
Not if the property is definable within the system, internal. And there's a similar version for infinitesimals. If a property holds for all positive infinitesimal hyperreals,
Numbers infinitely close to 0.
then it must also hold for some positive hyperreal number that is not infinitesimal. It spills over from the infinitely small to the appreciably small, you can say.
It sounds like a way to bridge the gap, to infer something about the non-standard from the standard and vice versa.
It is. The Wikipedia example shows using it to prove the equivalence of the standard epsilon delta definition of continuity with the non-standard one involving infinitesimals. It lets you transfer properties across that standard non-standard divide.
Okay, that makes sense. It links the familiar world to this expanded hyperreal one.
Precisely. So these concepts, different infinities, hyperreals, transfer, overspill, they offer a completely different yet rigorous way to think about analysis and infinity.
This has been, really illuminating. We started with Cantor showing some infinities are bigger than others, countable versus uncountable, the diagonal argument.
Right, then Hilbert's Hotel showing how weird countable infinity can be.
And then diving into non-standard analysis as an alternative framework, thanks to Tao's insights. The hyperreals, the algebraic field, the transfer principle connecting standard and non-standard worlds.
And overspill, linking the finite to the infinite within that system.
Plus, the trade-offs, complex spaces, maybe harder constant extraction, but potential wins in symbolic computation and formal proof.
It's a fascinating area.
So for you listening, hopefully this gave you some of those aha moments. Even if you don't remember all the terms, just grasping that infinity isn't monolithic, that there's this hierarchy, that's a huge takeaway.
It really challenges our intuition, which is built on finite experience. Mathematics gives us the tools to go beyond that intuition rigorously.
Absolutely. And it makes you think, doesn't it? How much does our everyday intuition limit us when we confront the infinite? And frameworks like non-standard analysis, are they just different tools, or do they offer genuinely deeper insights into these abstract realms?
That's a great question to ponder. Perhaps it sparks some curiosity to look more into Cantor, or the philosophical side of infinity, or even the technical details of non-standard analysis.
Lots to think about. Thank you for joining us on this deep dive.